Back everyone. So today I'm going to continue our discussions about reasoning. Recall, reasoning is all about taking the knowledge that we've learned from multimodal representations, local representations between elements of individual modalities, and also a line representation, taking into account multiple elements across multiple modalities. Now do you combine all this information in a principled way through perhaps multiple steps, through perhaps taking into account the knowledge of the problem in order to get the final answer. And we started reasoning, just a recap, with this very nice example, right? You take, for example, an image capture retrieval model. It works really well for cases you've seen before, like some plants surrounding a light bulb, and it fails when you bring in two just very simple switches on the second one, the light bulb surrounding some plants. And we saw that this was the, so all these current models like Clip, Wild, Wilbur, they all perform only at random chance, and they fail this compositional generalization problem. So you generalize the compositions of your input elements outside of your training data, outside your things you've seen before. We basically saw that to solve this compositional generalization problem, one principal way is to first define the structure, looking at how your big data, your whole image and your whole sentence breaks down into individual parts. The concept itself, being able to perform local alignment of plants and light bulb individually. Looking at the inference, which is the way that you combine plants and light bulb, in this case using the word surrounding, which is a spatial relation. And finally, all this comes only from knowledge from humans. Very difficult to learn from data. You need exponential number of samples to discuss the local elements. So typically, some amount of domain knowledge is required to perform robust reasoning with limited data. And we looked at some sub-challenges of reasoning. We looked at structure modeling as a big one. What is the right way to define a structure in which we compose individual elements into your final answer? Looked at temporal reasoning in the last lecture. We looked at memory networks. When all your data comes through time, and you want to look for these cross-modal interactions across time. We looked at hierarchical reasoning in the case of language expressed naturally as parse trees, some other form of data expressed naturally as graphs. How can we define methods that work well for trees and graphs? Today, we're going to look at interactive reasoning and structure discovery. If you don't know the structure, how can we discover the structure automatically from data? We also saw a glimpse of the second sub-challenge. What are the intermediate concepts you parameterize at each level of reasoning? In the most basic case, you can just define them as continuous vector representations to make them compatible with deep learning. We also saw examples of attention maps, and today, and next lecture, we'll look at more discrete attention maps and discrete concepts, for example, using language as an intermediate medium for reasoning. You recall the third sub-challenge is inference. We define the structure. We've defined the intermediate concepts. How do you actually compose these intermediate concepts at every level in the structure? That can be, again, through dense representations, but it can be also more principled, for example, logical inference or causal inference. And we'll talk about that on Thursday. And finally, all this only comes with some amount of either human knowledge or external knowledge from other data sets. So to recap, reasoning. 4 sub-challenges: modeling the structure, modeling intermediate concepts, looking at how we can infer more increasingly abstract concepts from basic ones, and what's the right amount of external knowledge to perform reasoning. And just to recall, last Thursday we looked at a temporal structure, hierarchical structure, and a simple introduction to continuous concepts. Today we're going to continue our discussion on structure through interactive structure and structure discovery. And on Thursday, we'll continue our discussion of concepts, discrete concepts, and also different ways of inference and external knowledge. So interactive structure. So in interactive structure, again, we have a concept. We have input data coming in across time. But the main difference between interactive structure and temporal structure is that the states, which are your input data coming in at every time step, is going to depend on your output from previous time. Whereas in temporal structure, the input data in the form of a sequence was fixed. In interactive structure, your new input data at the next time steps are going to depend on the actions you take previously. And as some of you are probably familiar with this is all about reinforcement learning. How do you deal with interactive structure, where the actions you take into the future are also going to be dependent on actions that you've taken into the past. So essentially, the first part of the lecture will talk about integrating multimodality into the reinforcement learning framework. Reinforcement learning gives us a nice formalism. All of these cases, where the state that your agent is currently in, the input that your agent currently sees is going to depend on previous actions that the agent has taken. So just as an overview, in a lot of this reinforcement learning plus multimodal settings, you're going to have multimodal data coming in at every time step. So over here, for example, you have an instruction that says, go to the green porch, and you have some visual environment in which you want to navigate an agent to actually look at the environment and go to the green porch. And perhaps at the input level, you want to do some local representation. You want to align the fact that you have a green torch to after references to the green torch. But you actually want to solve all of this by learning a reasoning policy. And a policy, which I'm going to define more formally later, basically tells the agent what action they should take at every given step in order to actually complete this goal. So again, the inputs are still multimodal. You're going to do some multimodal fusion and alignment. It's just how do you learn this policy? The reasoning step, how do you formally learn this policy in order to maximize this new objective, which is going to be a bit different from your classical supervised learning objectives. So as I mentioned, we're going to talk about our introduction to reinforcement learning. We're going to set up the basics. We're going to look at formalism for reinforcement learning based on Markov decision processes. We're going to show how to solve them and recent techniques for integrating deep learning into RL. And then we're going to revisit back the multimodal thing. How can we take these techniques that we've learned in RL and bring them into multimodal RL applications? So that's introduction. So RL is all about formalizing the fact that you have an agent that visits a set of states. The set of states can be defined as the environment. For example, your position in some game. You can move up, left, right, forward, and backward. It can also be, for example, you're playing chess. The set of states can be all the chess pieces in a game. The agent also sees a set of actions that they can take. And a transition function basically tells me if I'm in a current state and I take a particular action, what is the distribution of next states that I can go into, right? So I move forward, maybe I just go one tile forward, but sometimes it's not deterministic. It can be random. If I try to go forward, the environment can also bring me to left and right with certain probability. The reward function is a function of the current state, the action you take, and the next state you go into. And that's basically an output scalar from the environment that tells you, that tells you what reward I get by taking that action from that state and going into that next state. You're going to start in some start state, and there's some discount factor, which basically discounts the rewards. Reward that I get at a certain time step is this, and rewards that I get longer into the future are discounted by some certain factor. And the horizon is basically a total number of states and actions that I can take before the game ends. Sometimes H is finite, sometimes it can also be infinite. So you're typically always going to see this type of diagrams in reinforcement. There's some agent interacting with the environment. The agent takes an action A, which is given to the environment, and the environment spits out two things: the next state that the agent goes into, and the reward that the agent sees at that time step. And this new state then goes back into the agent's internal model, and you should take a next action given to the environment and go to a next state. So there's three key things you want to remember in reinforcement learning. One is the return. The return from a particular GT at a particular time step T is a reward that you take at a current or next time step, whichever way you index it, plus a discount factor of the reward one step into the future, plus the discount factor squared of the next reward into the future. And that's going to be one key difference in reinforcement from supervised learning. In supervised learning, you just make one action, you get one reward, you're done. You can maximize reward locally. For reinforcement learning, you can see a lot of challenges for maximizing cumulative reward. The fact that when you take one action, you want to care about the current reward you get, but also rewards into the future that you also want to maximize with respect to. Your policy is basically the output from reinforcement learning. You solve the problem, what people typically want is the policy, and that's a distribution over possible actions at a given state. It tells you what actions the agent should take from that state. And again, this can be deterministic. So at a given state, always just take that one action. It can also be a bit random. It can be a distribution over actions to take at a given state. And as I mentioned, the goal of reinforcement learning is to find the best policy that maximizes the long-term cumulative reward. So again, some key differences between reinforcement learning and supervised learning. I've alluded to some of these. In reinforcement learning, you have sequential decision making. You're going to make decisions multiple times. Every time you make a decision, it affects the local reward, but also rewards into the future. In supervised learning, you typically have one-step decision making. So you make one prediction and you're done. In reinforcement learning, because of the nature of your decision-making problem, that being sequential, you're aiming to maximize cumulative reward. Reward not just now, but also discounted rewards into the future. In supervised learning, you just maximize immediate reward. In reinforcement learning, because you want to maximize cumulative reward, one of the hardest challenges is the case of sparse rewards. When you take an action, you don't see a reward immediately, but you see reward long into the future. And how do you actually plan a sequence of actions that might be across a very long range of episodes before you finally see a reward into the future? That's called sparse rewards. In supervised learning, you typically get dense supervision. At every action that you take, at every category that you predict, you're going to get some reward in the way of your supervised objective function. And in reinforcement learning, sometimes it also becomes much more challenging when the environment could be unknown. For example, if I have a robot trying to traverse a building, you may not know what obstacle there are when you turn right and you don't see it beforehand. You may not know how long you have to traverse before you actually get to your goal. So these are all cases where the environment isn't known. And in supervised learning, you typically see everything. You see probably the whole image, you see the whole sentence, you see the whole video, and you try to make a classification. But despite these differences, just as a warm-up, can we just directly apply whatever we see in supervised learning that we know how to do directly to reinforcement learning? So one example is this, right? Let's say I want to navigate a self-driving car. The inputs are what the car sees on the road, your roads, your pedestrians, the sidewalk, and so on. And your goal is to output some actions telling you how I should drive the car. So how much I should put into steering, how much to accelerate, how much to brake, and so on. And one initial attempt we can do is you can basically just let an expert drive a car. Like all of us know how to drive, get an expert drive a car. And a car can basically record whatever a car sees at every time step and whatever the expert human did as an action at every time step. They accelerated in this setting, even curves, going to turn the steering wheel left and so on. So they can basically collect these trajectories, the start state, the action from the start state, the reward that you get, the next state, the next action, the next reward, the next state, the next action, the next reward, and so on. And these are collected from human demonstrations. And then you can basically do supervised learning. You can take in the states in this trajectory, and from every state, train a model to predict the expert action at that particular state. And this works pretty well to some extent, but there's still some very big challenges. One big challenge is our distribution mismatch, right? If you go to a state that you've never seen before through these expert demonstrations, then your car is going to fail. And it's going to fail much worse than supervised learning. In supervised learning, if you see an input that you've never seen before, you get a wrong action. That's all good. You reset, you start predicting the next input. But in reinforcement learning, because of the nature of the sequential decision-making problem, you see a bad state, you take a bad action, you go to an even worse state. And you take an even worse action, you go to an even worse state. So you're going to tunnel into some really, really bad states and really, really bad actions, and you're not going to be able to stop. Right? So all errors are going to compound much worse than supervised learning. It's going to be really hard to recover from suboptimal states. And of course, we know that in this case of self-driving cars, you don't want a self-driving car to go into some bad states and start taking some bad actions in the real world. So you typically can't test these models in the real world as safely as you can test for supervised learning. So hopefully that gives you some motivation to know that whatever we did for supervised learning is going to be quite insufficient for reinforcement learning. And it's going to be a new class of methods to solve these problems. So reinforcement learning, I'm going to define 4 quantities that are going to be very important. 2 on this slide, 2 on the next slide. And these are basically value functions. Given a particular state or given a particular state action pair, can I formally define how good that state is and how good that state is acting? So this quantity V pi of S basically takes in a state, pi, a current policy you have, and basically V stands for value, right? So in V pi of S is determined as an expectation under that policy pi. So basically following that policy, following whatever actions that policy tells you to do, the expected long-term reward starting at that state. And again, GT is important, right? GT basically captures long-term reward. And if you don't remember what GT is, it's basically the sum of your current reward plus discounted next reward plus discounted squared next reward and all into the future. So basically this quantity evaluates for a current policy pi and a current state S that I am, what is the expected long-term reward of that state following that policy? And that's a state value function. And likewise, you can define the action value function. Instead of just condition on the state, you can also condition on the action. Right? If I'm a current state S and I take a particular action A and I keep following my policy pi long into the future, what is the expected long-term reward given that I started at that state S and given that I took that action A? So that's under a given policy. You can then define the optimal, the one that maximizes over all policies. And it shouldn't be hard to see that if you have your value function for a given state, for a policy, you can then maximize over all possible policies to get the optimal state value function. That basically tells you for all policies, what is the essential optimal value for that state. Again, defined in terms of expected long-term rewards. And likewise, if you had a state value function, action value function for a particular policy, you could take an argmax or max over all policies to tell you the optimal action value function, Q star. And it shouldn't be hard to see that there's a lot of redundancy in this parameterization. You can actually interchangeably exchange through all of these quantities. We've seen that if you have a state value function for a particular policy, you can take argmax over all policies to get the optimal state value function. Likewise, if you had an action value function for a particular policy, you could take an argmax over all policies to get the optimal action value function. And it's also interesting that you can interchange between state value functions and action value functions. Right? If you have an action value function for all states, the state value function basically takes average over all of the actions, where the average is given by the distribution of your policy. Right. So for some actions, you take it more often. That probably is going to be higher. For some actions, you don't take it as often. That probably is going to be lower. Basically, an expectation under your policy of your action value function. And if you want to convert from your optimal action value function to the optimal state value function, that's just taking the best action. Right, so you can actually interchange between all of these variables. And therefore, solving reinforcement learning is basically amounts to solving all of these equations. We've seen that they're quite redundant, so you can just take one of them, your favorite, and try to learn that value. And you have your Q star, your optimal action value function for all states and actions, then you can find your optimal policy, right? The optimal policy for every given state is 1 for actions that fulfill the argmax over your possible actions and 0 otherwise. Right, so I have all these optimal action value functions for a given state. It tells me every action's value with respect to your long-term cumulative rewards. Then the action that best maximizes your optimal action value function should be the action you take in your policy. And if you choose not to obtain your Q star and instead obtain your V stars instead, you can still find your optimal actions, except that because the action variable doesn't directly appear in this equation, it's going to be a bit more challenging. What we can do is one step look ahead. So given a particular V star, and then I'm going to take, so V star tells me in the next subsequent states, the optimal value for those states, right? What you can then do is to apply the current action to get to those states. That's why I'm going to take an argmax over actions. For every state, take an action, go to the next states, and look at what's the discounted optimal state value function from those next states. And then you can probably take an expectation over your next states because the state transitions may not be deterministic. And the action that takes the argmax over this equation is the action that you should take from your policy. So essentially, from this current state, look at all the actions and the next states that you go into. And from the next state, you're going to see the optimal state value functions for those next states and pick the branch that gives you the largest one. So it sometimes also helps to see this visually. These gain trees are typically shown in reinforcement learning. And you can see in the cases, the white nodes being state nodes and the black nodes being action nodes. And then once you take an action, you go into next states. So you see another layer of white nodes. So in this case, what I'm showing is that you start with a white node, that's state S. You can compute your optimal state value function from that node. There's a possible set of actions that you can take. And for every action, that gives you to a new distribution of next states. Again, this could be deterministic. This could also be probabilistic if your transitions are probabilistic. And when you take an action and go to a particular next state, you're also going to observe a reward, right? That's the reward that we've seen. The reward depends on the current state that you're in, the action that you take, and also the next state that you go into. So using this recursive definition allows us to rederive some of the quantities that we've seen previously. You can see from the fact that your optimal state value function from this state is equal to a max over the actions that you can take from this state. And once you've taken an action, what do you get? The black node can be seen as the optimal state action value function at that action. And they can recurse further. We can then go down into the next reward, and your optimal action value function for your state and action is equivalent to the reward that you get from that state, taking that action, going to the next state. and then recurse the next optimal state value function from the next state you go into afterwards. So again, all of these equations basically can be derived from this tree, right? Starting from a node, you know it's optimal, so you take a max over the actions. And once you've taken a max over the actions, that gives you the action value function at this node. And this action value function at this node can be seen as the immediate reward, and then also the discounted reward for the optimal states that you go into. And the expectation is here because, again, some of these transitions from taking action into the next states may not be deterministic and could be random, right? And this is just basically writing the expectation over next states as the definition of expectation, summing over all possible next states and looking at the transition probabilities of going to those next states, given your current state and action. Right. So this perhaps does not the most math, but I'm going to stop here if anyone has any questions. Cool. So if we forget this equation, the easy thing now is just to draw this tree. And a key takeaway from drawing a tree is that you're going to draw one level of nodes for your states, another level of nodes from the actions that you can take from that state, and then the next level to the next states that you go into. And you can keep recursing over however many states and actions you take. All right. And then all the states that you have, you're going to define these optimal state value functions. For the action nodes that you have, you're going to define all the optimal action value functions. And then you can start recursing. And likewise, you can do this for your action value functions too. Instead of starting from the states and going into actions and next states, you can also start with a single action and going into next states and next possible actions. Right. So over here, this node is Q star S of A, the action value function. That gives you some reward and goes into the next states. And from the next stage, you can take further actions downwards. So you can define your optimal action value function as an expectation over the next states that you go into. When you take an action, you go into multiple next states. And inside the expectation for a given next state, you see the reward from the next state. And then you go into these next state nodes. And we know that the optimal value for the next state is given by the optimal state value function, right? V star of S prime. And the V star of S prime, as we saw previously, is equivalent to taking a max over the next possible actions you can take. And then it goes back to Q star of S prime and A prime. So again, you can define recursively all these functions, Q star and V star, with respect to each other. And finally, this last step is basically rewriting the expectation over next states S prime as a summation of the next states and the probabilities of going into those next states. And the good thing about this is that now that you define these recursive definitions, it actually helps you to solve some of these quantities in reinforcement learning. This is the recursive definition we've seen for V star. And if you don't know what V star is, you can basically find an iterative method to solve it. So you can initialize all your V stars at random, but you know that whatever V star function that you have has to satisfy this equation, right? And that basically means that you can solve, it's not like a fixed point equation, you can solve this equation by initializing your V star from one iteration, say K, and use that to iteratively update your V star for iteration K plus 1. Right, this is something similar that we've also seen in graph neural networks in the last lecture, right? You had a bunch of node embeddings for your graphs in your node, and they depend recursively on each other because the node is going to depend on its neighbors, and those neighbors depend on that original node. And if you have a fixed point equation with that same variable appearing on left side and right side of the equation, you can basically initialize at random, and at every iteration, use a previous iterate's estimate for that value to update the next iterate's estimate for that value. And that gives us the first algorithm for reinforcement learning. It's called a value iteration. So you're going to start with V star of 0 at a 0th iteration equals to 0 for all states. And I'm going to go through multiple horizons. I'm going to iterate in the environment to get next states and next actions. So K is going to define my iterations. And for every state S, I'm going to recursively update this equation using the previous iterate's estimate of my V star at K plus 1. Using that to update the next iterate's estimate for my V star, so V star at K. And eventually what you're going to get at convergence is you're going to get a sequence of V stars over all states that satisfy this recursive definition. Right? At every state, the V star depends on the V stars for subsequent states. You're going to get a full tree with V star that satisfies the convergence equation, the optimality equation. And at any time, if you want to test out your model, you have all these V stars. You can also obtain your policies. The policy, basically, as we saw with V star, you can obtain your policy with one step look ahead. Basically looking at, given a particular state, what's the best action I should take? I'm going to take every possible action. And for each of these actions, I'm going to look at the reward obtained by the action. And for the next stage that I go into, I'm going to look up the V star that I've learned to be optimal, the optimal state value function for the next state. So that's called the value, that's called, kind of looking at the current policy at a particular iteration. You can repeat this until it converges. But converging means that at every state, the optimal state value function satisfies this recurrence, and you're actually guaranteed to converge to the optimal policy. Any questions for this algorithm? In general, these are kind of called like fixed point methods. We saw it in graph neural networks as well. But essentially, when you have a variable and you know that variable should satisfy some optimality condition, so you saw that your V star estimates for your states should depend on your V star estimates of your next states, right? And if they're not equivalent, you can basically take the error and try to minimize that error. So that's what this is all doing, right? It's trying to minimize the error between your estimates of your V star S and V star S prime. I think, yeah, EM is kind of similar in the sense that you also kind of, I think it's kind of similar to EM, but not exactly. Right. So instead of doing it for a V star, you can also do it for a Q star. We saw that there is optimality equation for Q star as well. For Q star and SA with respect to Q star of your next states and next actions. And again, you can do this iterative method. You can have an estimate for your Q stars over all states and actions. And for your current estimate at Q at iteration K, you can use that to update your next estimate at iteration K plus 1. Right. And repeat in the same way, you can also eventually get your estimates for your Q stars across all states and all actions. And again, this is just going to be a quick crash course. Katerina teaches a full course on deep RL at CMU, and they go into value and policy learning for a lot of lectures. So you can check that out if you want more details. So to summarize, at least in the first attempt at reinforcement, if you have a fully known MVP, and fully known meaning that you know all the transitions, the exact probabilities of all the transitions, you can enumerate the states, you can enumerate the actions, they're all small and discrete, and you know all the rewards. Then what you can do is you can define these Bellman optimality equations. You had an optimality equation for your Q stars for a state and action with respect to other states and actions. You also have an optimality equation for your V stars of states with respect to other states. And once you have this optimality equation, you basically iterate, initialize with something and iterate to get the optimal Q stars and V stars. So those algorithms are known as Q value iteration and value iteration. We've also seen Q star not the optimal version, but also conditioned on a policy. And these are called Bellman expectation equations for a given policy. And it shouldn't be a surprise to you because we can interchange between all these four quantities. They're also equivalent algorithms if you just do it with respect to a policy instead of with respect to the optimal Q stars and V stars. So that's known as Q policy iteration and policy iteration. The ideas are very similar, just that optimality equations are a bit different. And basically, if you repeat this iterative process until your policy converges, you're guaranteed to converge to the optimal policy. And as you see from the questions, there's some limitation. Right? It requires you to store and iterate all your states and actions. You have to be small and discrete. And it also requires knowing the transitions. Basically, you have to fully observe the MDP and know all the transitions between states and actions to next states. So if you don't know these transitions, this is the key issue. Right? You can't take an exact sum over all possible next states without knowing the transitions. What can we do? Well, we all know how to approximate sums with expectations, right? And instead of computing the sum exactly, you can convert it to an expectation. And with an expectation of our next states, what you can do is basically just sample a bunch of next states without knowing the exact number. Just sample the next states and see what, sample a bunch of states and actions and just see what next state you go into, right? So that gives us a first approximate algorithm for reinforcement learning. Given a particular state action pair, just apply it into the environment. So take the state S, take the action A in the environment and see what next state it goes into. And given the particular next state it goes into, I'm going to replace the expectation with the actual samples of your next states. So again, the next two equations are the same. This is basically again considering the optimality equation for your action value functions. The right-hand side is basically what you want the next state to predict, the target value of your action value function for your next state. And the error is basically whatever my Bellman optimality equation was, the left-hand side minus the right-hand side. Right, you want to minimize this error. So essentially what all we've done here is to replace the expectation over actual next states with a sampling over the next states. And you get another version of iterative algorithm. You know your particular estimate at a kth iteration for action value function. To get the k+1th iterate, you basically compute the error. And the error is the difference between the left-hand side and the right-hand side. How much your current estimates for a particular state and action differ from the same estimates for the next states and next actions. We know that at optimality, this side should be equal, right? This big equation here should be equal. The left-hand side and right-hand side are equal. So whatever that is not equal, you take the difference, treat that as the error term, and minimize this error term with respect to some learning rate. Right, so that gives us what we call a tabular Q-learning. And starting from, for all states and all actions, initializing your action value function, Q0, start with some initial state, and keep repeating until you converge over all iterations. For every state, sample an action A from the current policy to get a next state. If S is terminal, then there's no next state into the future. Your target is just the reward for your state and action into the next state. Otherwise, if S is not terminal, then what you want the current estimate to be equal to is the current reward that you take plus the next, the estimated action value functions from the next states. And if your left-hand side and right-hand side are not equal with respect to your Bellman optimality equation, then basically take the difference between your left and right-hand side, treat that as the error, and try to minimize it. And that gives you your next update at the next iteration for the optimal action value function. And just one small note, given a current policy, how can I actually sample my next actions? There are a couple of options. You can just choose random actions. You can choose the action that best maximizes your over your action space given a current policy. So that's a greedy selection of actions. Or people found that something in the middle works best. They call this epsilon greedy. And this epsilon greedy term is perhaps one of the most important keywords in reinforcement learning. It basically balances exploration and exploitation. At the start, you're going to have very poor estimates of your action value functions, your Q stars. So if you follow your policy at the start, you're just going to start getting into really bad actions and really bad states and really bad actions subsequently. So that's why at the start, you want to estimate not based on your estimates of your Q star, but just do randomly. Right? Randomly explore the environment, look at all possible actions that you can take and see which actions are good. And that gives you a higher chance of actually picking an action by luck that's going to get into next states that have good rewards. Right? So they call this epsilon greedy, right? Your policy, the set of actions you take given a state S, follows with probability 1 minus epsilon, actually taking the best action, and with probability epsilon just taking something random. And then you can gradually decrease epsilon as your policy is learned. It's at a really high epsilon of 1, which means that you're always taking random actions. You're fully exploring, trying to find actions that give you good rewards. And as you slowly start learning, your estimates for your Q star is going to be really good. Then you can rely more on your policy that maximizes your Q star instead of taking random actions. So therefore, you want to sample these actions A using an epsilon greedy method. So any questions about this extension? Nothing much, just that instead of actually computing the expectation over all possible next states and computing the equation exactly, I'm going to replace the expectation with samples by looking at the environment and see what next states I get and approximating this equation, something like gradient descent, computing the error and minimizing the error with respect to some learning rates. Cool. No questions. There's still some issues here. We cannot solve the issue with transitions. We don't know the transitions. We simulate them. We see what next state you get into. You approximate the expectation. But it's still tabular in the sense that you have to keep a full table of across all your states on the rows and all your actions on your columns, right? So this still requires you to have a small and discrete set of states and actions. It doesn't really scale to images and text being our actions and states. And also doesn't allow us to generalize to unseen states. Right? If you have this table, you're not really going to be able to infer something about your Q stars for states that you haven't seen before. And all these things are things that we want to ideally have. So the next extension then is deep Q learning. And we use deep neural networks to approximate this table of states and actions. And the idea is very simple. Instead of having a table for your QSAs with respect to states and actions and having all the states and actions independent, I'm going to basically define a model that takes in states and actions through some neural network parameters W and output an estimate for my states and for the optimal action value functions for those states and actions. And you can do it in two ways. You can take in states and actions both at the same time. You can output QSA, or you can just take in one state and output QSA over all your actions. And sometimes you want to pick this, sometimes you want to pick this. This typically is going to be a bit harder because it requires the actions are still discrete. So whatever number of actions that you have, this requires each action is one branch in the output network. The first case might work better if your actions are high dimensional and continuous. So if your actions are continuous, or could be even language, you can take in a pair of your states and actions and just output one QSA. And then you can immediately see how this can be beneficial. Whatever neural network function approximation you apply, it can be very flexible. You can choose the best network to encode your states and actions. So that allows you to work with high dimensional and continuous states. And also, it also generalizes to new states. If I see an S during training and I estimate QSA for that S, if I have a similar S prime during testing that's similar in neural network representation space, you should still be able to give good estimates of your QSA for those new states. But otherwise, apart from this approximation, the learning method is very similar. Again, you have this Bellman optimality equation. We know that a Q stars for your next states and next actions to respect your Q stars for your states and actions. Whatever error term, I'm just going to minimize it. Right. So right-hand side, we know that this should be equal. I can treat the right-hand side as a target. And whatever difference between my left-hand side and the right-hand side, I treat that as my error term. I can take the mean squared error and try to minimize this by greatness. Ideally, you want this error to be 0. And when this error is 0, your left-hand side and right-hand side of your Bellman optimality equation are exactly equal. So the learning is the same as whatever you've seen previously. And we know that we've seen this learning method before. In the case of tabular Q learning, we know that it converges when your Q stars SNAs are in the form of a table. But when you immediately try to apply neural networks, there's some challenges. And the idea is that it diverges because of two things: your correlation between samples and non-stationary targets. So what is correlation between samples? So typically in reinforcement learning, you're going to collect the data set. Your current state, next action, next state, and then next action, next state, next action, and the further state, and so on. And you basically collect all of these samples and you put them into a data set. But one key issue with applying deep learning to such a data set is that all of these data points are correlated with each other, right? Your second data point is almost exactly dependent. It's almost repetitive, right? The state with respect to the previous data point. And likewise, the third one is going to be exactly repetition of the second. And that can be seen as equivalent of doing image classification. You're going to see a bunch of cats, all cats in one batch, and then you go to another batch, you have all dogs in some other batch, and you go to another batch with all tables and so on. So that's going to make the network really hard to learn because you're basically just maximizing logits, the same logits for one batch, and maximizing a completely different set of logits for some other batch. Right? Typically in neural networks, you want to assume that your samples are IID. So correlation basically breaks the IID assumption. So one simple thing you can do is, instead of just doing this online by updating one sample at a time and having it correlate with previous samples, just take a bunch of data points, states and next actions and next states, take a bunch of them, make it really large, and then just shuffle them, right? Shuffle them and sample a random mini batch. And that's what people call experience replay. You're gonna have a big batch of samples from the environment. They're correlated at the beginning, but if you shuffle them and you sample a mini batch, if it's big enough, it's going to be approximately an IID sample from the true distributions of states and actions. And again, as you sample these points, your states and next states, you want to do exploration. You want to do all the ideas from epsilon greedy. You want to bring all of them here as well. So you start by random exploration when your estimates of your Q star are bad. And when you slowly get better estimates of Q star, you can follow actions by maximizing the actions of your Q stars. So another issue that we saw previously is the fact that your targets are non-stationary. So what does that mean? One interesting thing you see here are that you're basically training a network to taking your states and output your Q stars, right? But these Q stars are changing. The Q stars that are learned at the first iteration is going to be different from the Q stars that you learn at a second iteration. And the analogy that you can think about is that instead of having a network with a fixed set of labels into image categories, the labels that you want to predict change every time. And obviously that's going to be very challenging for a model, right? So what you can do is you can do what we call fixed targets. Essentially, instead of updating your Q stars at every iteration like you would for previous methods, I'm going to just keep it fixed, accumulate the gradients for perhaps 1,000 steps. And once you do 1,000 steps, then you finally update. So instead of having the targets change at every iteration, you only changes perhaps every 1,000 iterations, right? So you fix the target. You can see that as the weights minus, so weights from previous, and you're just updating the Q network. You just update one set of the equation using gradient descent, and after perhaps 1,000 equations, you finally take your updated W and replace your previous W minus, right? So do that over only after 1,000 iterations instead of every iteration. Cool. So that basically summarizes deep Q learning. Taking all the ideas of Q learning, we saw that it was tabular, fixed set of states and actions, instead of keeping a table of all states and actions as approximated using a neural network that takes in your states and outputs your Q stars for every state and action. But two big challenges. One is correlated samples. So you want to take a huge batch of samples from your simulation environment. If it's big enough, you can shuffle it, sample a random mini batch that kind of decorrelates your samples. And the other issue being that of non-stationary targets. You don't even output predictions to be changing in every iteration. So you basically keep and freeze the set of weights for multiple iterations, accumulate all the gradients, and only update your targets after perhaps 1,000 iterations. Cool. Any questions so far? All right. So everything that we've seen so far can be it's just one small slice of reinforcement. Again, check out the course at CMU and other places if you want a full primer to RL. And everything that we've seen is just one dimension in this dimension called value-based methods. Again, we started with state value functions, action value functions, and therefore the name is state value-based methods. And the whole idea of doing value-based methods is to learn these value functions, learn the values of every state, learn the values of every action. If you have that, you can then infer what is the best action to take given the estimated values. The alternative is policy-based. So in policy-based, you don't care about estimating the values. You're not going to keep your V stars, your Q stars. You're just going to try to directly learn the policy, right? You're going to parameterize a policy as just a distribution of actions given some particular state and given your neural network parameters data. So I'm just going to also go very quickly into how we can look at these policy-based methods for reinforcement learning. And then we're going to talk about a combination of both. So learning a policy directly, there are several benefits. Often learning a policy can be simpler than learning your Qs and Vs. One classic example people use is training a robot to grasp an object. Right? If you think about how you can do that, if you want to write an MVP of your robotic arms, there's going to be many particular joints in the arm. Right? And that can be very difficult. There's many Q stars and many V stars. It can be very high dimensional, but sometimes your policy can be much easier. Your policy could just be something like closed hand and open hand. You can basically combine many of these local states together into a more global policy. Sometimes directly learning a policy can be easier. We've seen that V doesn't directly prescribe your actions. If you have all these V stars for particular states to get a particular policy, you need to do one step look at them. Right? You have to look at all the actions that you can take from this state. And once you go into next states from those actions, then you can apply your V stars for those next states. So that basically needs you to at least be able to enumerate all your states and know some amount the transitions to next states. And even if you solve Q star, that gets you to your policy easier. If you have Q star for states and actions, you can just take A that gets the argmax and do epsilon greedy. But even sometimes doing this argmax over A can be quite challenging, right? If your A is continuous or it's really high dimensional, taking the argmax is non-trivial. So therefore, people have looked at directly just learning the policy, like ignoring the V's and Q's, just directly learning your policy pi. So here's one example we're going to for the next couple of next 20 minutes. How can we directly learn the policy? So I want to train an agent to play this game. One side is a human, and perhaps the right side is a human, the left side is an agent. Very simple. Just move up and down. Try to prevent the ball from going into your side of the court. Now what I can do is I can find a model that takes in these images, which is the current state of the game. So if I freeze this game, it can be perhaps an 80 times 80 image. You can go to a hidden layer and just train a model to predict the actions, like whether I should move up or down. And because these two are binary, you can just have one output neuron predict the probability of moving up. And your network basically receives some reward. +1, if you score a point against the opponent, you put the ball over the opponent's court. And -1 if you lose, if you get scored against, that the opponent puts the ball into your side of the court. And then the goal is just about learning these parameters. So in a simple case, let's just assume that for every state that we see, at every intermediate state of the game, we see the optimal action. Right? For this particular state, you should go up. For this particular state, you should go down, and so on. Then basically, this reduces to supervised learning, right? Taking a particular state and maximizing the log probability of producing those ground truth actions at that state. Right? You can basically define your binary cross entropy loss, which is the log probability of the correct action, and train your model to maximize this log probability. But of course, we know that we don't have these labels. Right? We don't have the label of going up and down every time. So what should we do? One thing that you can do is just let the model play. Right? Let the model play. The model is going to take a sequence of actions, down, up, given its particular, following its particular policy. And perhaps for some lucky reason, you apply this policy to your start state, and after a sequence of interactions, you see that you won. You was able to put the ball into the opponent's court. You're just going to keep repeating this, right? For some particular sequence, for some particular trajectories, it's going to win. So for some particular trajectories, it's going to lose. And every trajectory involves many actions before you finally see a reward. Right? So the model might not be sure why exactly this sequence of actions led it to win, but I don't care. I'm just going to uniformly increase all the actions for that trajectory, because eventually you did well. I'm just going to increase the probabilities of all these actions. And again, I'm not sure what I did here in this sequence of trajectories that led me to losing, but it must be bad. So I'm just going to decrease all the actions in that trajectory, right? Just pretend every action we took in green was the right label. So I'm just going to increase those probabilities, log probabilities, and assume that all actions that I took in this red trajectory was incorrect. So I'm just going to decrease all those trajectories. And finally, just one small detail, I can add this down. If I saw that this action led me to observe -1, so I'm going to assume that that action, which immediately led me to the negative reward, should be penalized the most, and actions belonging to the past should be discounted less. And that seems natural, right? It was closer to when the -1 reward happened. I should penalize it more, and that basically takes into account the discounting, right? So this was -1. I'm going to put this as -0.9, put this as -0.9 squared, and so on. So with a discount factor of 0.9. Yes. We'll get into that soon, right? Right now, AI is just its discounted reward. You're one step further ahead of me, because that goes into kind of variance reduction, which we'll look at in a little bit. But right now, no variance reduction, just the raw rewards discounted. And that actually gives us a very simple algorithm, and we're going to look at why this works. But it's actually very simple. So initialize a policy at random. That's your neural network that takes in your states, produces the probability of moving up. I'm going to just keep collecting a bunch of rollout trajectories using my current policy. Some are going to be luckily good, some are going to be lucky, some are going to be bad. Most are going to be bad. But a key again is to use epsilon greedy, so that I explore enough, so that I'm at least increasing my chance. I have at least random chance of observing a sequence of actions that leads to a good reward. And then I'm just going to do something very simple. I'm just going to define the objective function as for all the trajectories that I want at the end. I'm going to increase the log probabilities of all the actions in that trajectory that eventually led me to winning. with some discount factor, A. And for all the rewards trajectories that I eventually lost, I'm going to decrease the probabilities by multiplying -1. So minimizing the probabilities of taking all those actions that led me to lose. And if you observe what's happening here, it doesn't require any transition probabilities. It doesn't require them at the beginning. We don't have to approximate them using expectations. It doesn't require me to estimate my Q's and B's because we're not doing value-based learning. But what we're actually doing is just directly learning the policy. And this actually works surprisingly well. You can train a model after a bit, it starts playing Pong reasonably well. And then the core question is, why does it work? Why does this simple method work? And why did I spend so much time introducing all these complex optimality equations if this works? So there must be some disadvantages to this method as well. So the last two slides is math in this method. This method is essentially called policy gradients. And to see why it works, we can formally define a class of parameterized policies. So each of these pi is given with respect to some parameters theta. So pi could be a neural network, in which case theta would be the neural network parameters. And you basically want to find the best policy, right? To find the best policy, the best setting of your weights in this neural network, you also have to define a value for each policy, right? And the value, basically, as we've seen, is the expected long-term reward following that policy, right? If I take this policy, I go into next states and next actions, and I accumulate all the rewards with some discount factor long into the horizon, long into the future. So we've seen all these trajectories. The trajectories are basically states and action pairs. You can write out a probability of a trajectory, probability of your taus. That's basically equivalent to taking policies under your policy, the actions given your states, and also the transition probabilities of your next states given your state in action, and multiply all of them together across all your time steps until you finish, right? So basically a product of all your policy parameters, policy probabilities for the actions in the trajectory, and also all the state transition probabilities from states to next states. And again, the reward of the trajectory is basically the discounted long-term reward. So you can then rewrite the value of each of these policy parameters theta as an expectation under trajectories following your trajectory distribution given by your policy, which is the probabilities of your trajectories. And inside the expectation is the reward of your trajectory. You basically want to maximize the reward of your trajectory sampled under the trajectory distributions given by that policy. And if this is the objective function, how do you find the best data to maximize the objective function? You can do something very simple, just gradient ascent. You just want to be able to take the gradient of this function. And once you can take the gradient, you can iteratively update with respect to the gradient to maximize this function. So then the question becomes, how do you take the gradient, right? So you know the expected reward of the trajectory under all trajectories from the distribution. That's equal to this integral. Integral over trajectories, the reward of a trajectory, and the probability of that trajectory. If you want to take the gradient, you want to take gradient with respect to theta, right? So you can move the gradient of theta with respect to theta into the integral, because the integral only depends on tau. But then you're going to be stuck with this gradient with respect to your theta, the probability of your trajectory. And what does the probability of a trajectory look like? That is your product of all of these probabilities, right? The product of your policy probabilities, taking those actions given by your policy, is also a product of all your state transitions from states to next states. And if you want to take gradient with respect to theta, this is going to be really big, really intractable. You got to do chain rule over like all of these probabilities, like many, many times. But what can you do? You can use a trick, which is that the gradient with respect to theta of the probability, you can multiply by the probability of theta on the top and the bottom. And this term, the gradient with respect to your theta p over p, is a gradient with respect to theta log p, right? By definition of gradient of log. And if you put this back into your integral, what you basically get is an integral over your trajectories, the reward of a trajectory, the gradient with respect to theta, the log probabilities of the trajectory, times the probability of the trajectory, integral over d theta. And you can observe the integral over theta, probability of theta d theta is just an expectation over theta. Integral over tau, probability of tau d tau is basically expectation over tau, your trajectories. And what's inside the expectation is the reward of a trajectory times the gradient of the log probability of that trajectory. And if you actually take log of the probabilities of those trajectories, it used to be a product, but a log of a product becomes a sum, right? A sum of logs. So basically getting a sum of log of your transition probabilities plus log of your policy probabilities of the actions. And when you differentiate with respect to theta, you see a very nice thing. All of these log probabilities of your state transitions go away because they're constants. They don't depend on theta. And what you actually get in the end is just an expectation. It's just a summation over your gradient with respect to theta, your log probabilities as prescribed by your policy. And you don't get any term that depends on your transition probabilities anymore. So therefore, the gradient with respect to theta is an expectation under your trajectory, but that can be approximated by a sum. And what's inside this sum is the reward of a particular trajectory and the log probabilities as prescribed by your policy of actions under that trajectory. Right? Log probability of your AT given ST. And this actually recovers the equation we started off through our intuition. You're basically saying that I'm going to take a gradient, and what does my gradient mean? If the reward of my trajectory is high, because I was lucky, I got a trajectory that won the game in the end, the reward of my trajectory is high, I'm going to try to push up the log probabilities of all the actions that I saw in that trajectory, all the sequence of actions. If the reward of my trajectory is low, I got a trajectory that eventually led me to lose the game, I'm going to push down the log probabilities of all the actions in that trajectory. And that's exactly as we derived as our intuition for us at the beginning, right? We have a bunch of trajectories, some of them won, some of them lost. I'm not going to care about the intermediate actions. I'm not going to try to decompose the reward. I'm just going to uniformly increase the actions in the trajectories that I won and uniformly decrease the actions in the trajectories that I lost. And that actually gives us the reinforced algorithm for directly learning the policy. I'm going to start with some parameterized model pi for my policy. It can be a neural network taking in states S and outputting a distribution over your actions with parameters theta. We initialize the network, and I'm going to keep repeating and generating these trajectories, states, actions, following a policy. Again, you want to do epsilon gradient. You want to explore randomly sample actions at the beginning, and when you slowly start getting better estimates for your policy network, then you can better follow your policy. But from each step, I'm going to compute the return, which is the reward of that trajectory. And I'm basically just going to optimize this objective, right? The reward of my trajectory times the log probabilities of the actions in that trajectory. If my rewards was high, if my, discounted rewards were high, I'm going to maximize the actions in those trajectories. If the discounted rewards of the trajectory were low, then I'm going to minimize the actions within that trajectory. And this actually seems very simplistic because you're basically assuming that my trajectory can be very long, right? It might take hundreds of actions before I see a +1 at the end. So uniformly kind of increasing the all of these 100 actions before I see the reward seems kind of naive, but an expectation averages out. There's no disadvantage to this. This assumption basically means that you need to see many samples, and it's much less sample efficient with all of your value-based methods. Another issue is that if your sequence of trajectories are actually very long before you see a reward, then naturally this assumption doesn't hold and policy gradients work less good. Another issue is that this suffers from high variance, right? Because credit assignment is really difficult, as mentioned. If you see a bunch of 100 actions before you actually see a reward, how do you actually determine which action was useful? So one intuition you can use here is that the raw reward of a trajectory isn't actually that useful. So if I have a different game where all rewards are positive, it's just that some rewards are more positive than others, then directly applying this approach, you're just going to push up the probabilities of all your actions in the environment. So it's not so much about the raw rewards, but the relative rewards, right? Whether the rewards are higher or lower than some average reward. So one easy idea is to introduce a baseline. The baseline can be some average reward depending on the previous rewards, right? So instead of just taking reward of a trajectory, do reward of a trajectory minus some baseline. And there's some easy ideas for baseline. You can do an exponential moving average of your rewards. Like kind of what we saw in memory methods. The exponential moving average basically smoothes out the fluctuation, just keeps the moving average of the rewards. And then you can see whether the next reward I get is much higher or much lower than this baseline. and use that to weight the reward and policy gradient instead of the raw rewards. And a better baseline is actually combining with something we've seen previously. We've seen previously how to compute our Qs and Vs, right? Qs basically tell us the optimality given that state of taking a particular action. And Vs tells us just in general what's the optimal, the cumulative reward from that state. So your QSA minus VS gives you a very nice intuition of how, in expectation, taking this action is good from this particular state with respect to cumulative long-term rewards. So if this value is large and positive, that means taking this action is very beneficial given this state. And if it's small or negative, well, it can be, small or negative, then you don't, this action is probably not a good action to take. So that means you can get this estimator. Right? Instead of having the raw trajectories or trajectory minus the baseline, you can basically estimate your states, your Q star and V star for every state in action, and basically just look at how much these particular actions improve your state value estimate. So for actions that improve this quantity by a lot, I'm going to increase the probabilities of those actions. And for actions that don't increase this quantity, then I'm going to decrease the probabilities of those actions. And therefore, you can combine these two methods. You can combine both value learning and policy learning. Given a particular input, you can first have some parameters that share layers. These are general function approximations from images. And then you can output two things. Your value function, which is estimate of QSA, and directly learning the policy, which is pi. You can then do two things. This is basically called active critic methods. The critic evaluates how good the action is through your estimates of Q, and your actor decides what actions to take using a policy pi. You can update your critic using everything that we've seen in deep Q learning. Again, we call it optimality equations, minimizing the difference between the left and right-hand side. That gives you good estimates of Q. And for your actor, you can optimize your policy using policy gradients, using what you infer from Q. Right? So actor will decide what to take. Again, an estimate of how good that action is based on your estimates of Q stars and V stars. And then if this is good, increasing the probabilities of those actions. If it's bad, decreasing the probabilities of those actions. And again, all the ideas from Q learning apply here. You want to do exploration, that's epsilon DD. You want to have an experience replay to decorrelate your samples. You also want to have fixed targets, so your output doesn't change all that often. And likewise, all the ideas for policy gradients apply here. You want to do variance reduction by applying this baseline. So to summarize, very small bits of reinforcement learning. We looked at value-based methods that directly learn your V stars and Q stars with respect to these optimality equations. And we saw methods of learning them. You can do value iteration and policy iteration in a simple case, but we saw some challenges in the case of not knowing the transitions or your states being high dimensional and continuous. So we extended some of these ideas to deep Q learning. For policy-based, you can ignore learning of the value functions and just directly learn the policy. And we saw how we can use policy gradients to do that. But there's some issues. Typically, policy-based methods are going to be less sample efficient and work less well if you have very, very long horizons. And finally, we saw kind of combining these two methods into active critic methods. The actor learns the policy through policy gradients, and the critic estimates the Q values using Q learning to estimate how good your actions are. So that kind of combines the benefits of value-based learning and also kind of solves some of the problems in policy-based learning because it introduces this baseline, this running baseline that you can compare to. Cool. I think that's all. Wait, we have until 11:30? Okay, perfect. So yeah, any questions about reinforcement learning basics at this point? Again, great set of resources by Katarina, who teaches the full course at CMU. But yes, back to reasoning. So we took a long detour, looked at some of the basics of reinforcement learning. And but all that was still to get us back into multimodal reasoning space, right? And if you call multimodal reasoning, it's about taking some of these environments which have multimodal data. You have visual environment, you have perhaps some language instruction that you want to execute. How do you take all this, do multimodal learning, do perhaps reinforcement learning to best learn the policy in order to learn an agent that can solve the task in this multimodal environment? So this survey paper is actually a very nice one. It basically covers at least back in 2019, the state of the art in applying reinforcement learning informed by natural language. And it basically decomposed two general sets of methods. One is task independent, which is, it doesn't really depend on a task. There's certain things about language that are important, right? For example, the fact that a key opens the lock, a key has to match the lock in order to open it, and so on. These are task independent, just general information about knowledge. You can try to integrate that into your RL environments. And there can be also task dependent usages of language in reinforcement learning. And one big one is language assisted. So the environment itself doesn't really use language, but language can help. Right? Language in the form of domain knowledge can help. And language conditional, where the environment itself inherently needs language. If you want to follow an instruction, or if you want to answer a question about the environment, then language is essential. Right? And that's language conditional. So just going through some examples. One big class of language conditional are is instruction following. We have some visual environment, and there's some instruction. I go to the green torch. And in many of these settings, these environments have to be some simulated environment where you can procedurally generate locations and colors and sizes of these green torch. And you basically want to make sure your model generalizes, right? You might see some environments during training. You go to different environments during testing. There's different levels of occlusion or different number of objects during testing. There are also cases where there's a train and test differences in your instructions. So you want to go to the red torch during training, but you want to go to the green torch during testing. So you're actually checking that you're learning generalizable features. And if you really think back to all the core technical challenges, this is essentially representation of fusion and representation of alignment. How can you ground objects? So you can use all of the ideas there. How do you segment your sentence to get the fact that green in your words matches green things in the object, in the image, and so on? And how do you learn compositional representation so that you can go from green torch to red pillars and red objects, and so on? But essentially what this paper did was to define a very simple fusion model based on data attention. You've seen all this representation of fusion, where you're learning an attention vector from your instruction representation to your image representation. And once you do that, you can then learn that multimodal representation and then go into whatever reinforcement learning policy you choose. In this case, it goes after critical, as we just talked about. So this multimodal representation can be used to learn both the value function for the critic to evaluate how good your states and actions are, your cues, and also learn a policy function to directly learn the policy using policy gradients. And this works pretty well, right? It starts by training on easy ones, where all of the objects in a row fully observable. You don't even have to turn around. It goes into more medium settings where there's clutter and occlusions. And it goes into really hard settings where you might have to, turn around the agent's first-person point of view in order to find the target objects. And again, you can do all the interesting things in multimodal representations. You can look at, for example, all the attention maps learned by the attention function. And they found that, they devised a way to make sure that this was compositional, right? There's a certain set of feature activations that just represent armor. There's a set of feature activations that just represent pillar and other objects. There's a separate set of representations that represent your colors, right? And that actually enables you to do compositional grounding, compositional generalization across different colors and different objects. Another set of problems is in body QA. So in this case, you have a robot that's navigating around a house, and you're basically asking a question to the robot, and the robot has to first identify that particular object you're asking about in a question, for example, the car. So it has to navigate around before answering the question, right? So this kind of extends, visual question answering, where everything is fully observed, into the embodied case, where you have to do navigation on top of question answering. Going into more language assisted RL, so we call language assisted RL, the environment doesn't need language, you can solve it without language. And typically some of these very challenging environments like Montezuma's Revenge, it's a very interesting one because it really exemplifies the sparse reward problem. You have to take multiple steps, thousands of steps, before you actually observe a reward at the end. And some of these intermediate steps is going to be very non-trivial to AI, right? It requires you to know that you should collect all these keys. You should know to avoid enemies, to jump over enemies. And once you have keys, you should know to eventually open the door and so on. So some of this, intuitive to us humans, very difficult for AI to learn. and made worse by the fact that you're very sparse with words. So what can you use with language, right? Or other multimodal inputs? You can do something called reward shaping. Reward shaping by adding auxiliary rewards is a general way of helping you solve sparse reward problems. Instead of just relying on the reward from the environment, just add intermediate rewards to things the agent completes that you know to be good. So for example, if you jump over the skull, that's a good thing. You're avoiding the enemy. Give it an external reward. If it collected a key successfully, give it a reward. If it used the key to open a door, give it a reward. So you can use all these reward shaping to help your model learn. And typically many of these reward shaping examples are in the form of natural language. It can come from, in this case, it was from Amazon Mechanical Turk. They got human players to play the game, annotate the important sub-steps, and then you can start by parsing these and using this as intermediate reward. And sometimes you can also use instruction manuals. Like, if you have an instruction manual teaching you how to play the game, you can use that as a form of language to also add additional rewards. So here I'm showing the example of this civilization game. Again, a very challenging long-term reward game. You got to build all these settlements. You got to collect wood, get food, increase your population, fight with other settlements to get long-term rewards. And you can basically use instruction manuals as a resource to shape intermediate rewards, right? So this paper over here talks about, for example, firstly choosing relevant sentences in the instruction manual. A lot of the sentences are going to be not super useful. Choose a relevant sentences based on whether it contains these important tokens, like grassland. And then it starts by labeling these words into things that you can use to inform your actions. For example, building or collecting or growing food, things that are state dependent. For example, grassland. Grassland is part of the state. What type of things can grow in grasslands and how do you harvest things in grasslands and so on, or background knowledge. So yeah, I'm not going into details, but you can check out this paper and a lot of other recent papers that come up on how do you actually parse these instruction manuals as a form of language, do alignment with the environment, and use that to shape your rewards in reinforcement learning. So to summarize, several examples of interactive reasoning. A lot of them centered around language and reinforcement learning, but you can think of audio plus reinforcement learning, touch and tactile sensors and other modalities in the case of reinforcement learning. But all these methods can be categorized into instruction following, where the instructions are essential to the environment. You want to follow the instructions to solve the task. Embodied learning, we're extending your QA tasks into the requiring navigation, right? Navigating around the environment before actually observing the object and answering questions about the object. Reward shaping by either getting some amount of language data to influence intermediate rewards, and also in general using language as domain knowledge. Cool, that's all for today. Just as a very quick recap, we looked at temporal, hierarchical reasoning last Thursday, continuous concepts. Today we looked at interactive structure modeling. Didn't have time to get into structure discovery, but structure discovery, we're going to talk about it on Thursday, and we're also going to look at discrete concepts before going to inference and knowledge. But yes, thanks everyone. Any questions?